So let me just give you a little bit of background about what we're doing here. So this will make more sense. I think it helps to know where we're going with this when you're setting something up. So the next unit is going to include portions of chapters 3 and 4, and we skip around quite a bit. And I'm going to do this a little differently than we're going to deviate from the textbook quite a bit. What it has to do with is solving linear systems, and you've done this. Now we're going to look at this in a couple different ways. We're going to do some algebra. We're going to start off with a graphing calculator approach, and then we'll move quickly into reviewing some solving linear systems using algebra, which you've done. You've done that a lot. You'll remember it when you see it. If you're given two lines, you called them, the methods were substitution, and then I think the other one you called elimination, right? And we reviewed this last year in geometry too, so it's stuff that it'll come right back to you. When we start to ramp up those linear systems, though, from small ones where you have just two systems with x's and y's to bigger systems that have more variables, the algebra starts to get difficult pretty fast. When you get into really big systems, if you got into like a system with 10 variables and 10 equations, that gets to be really difficult and very confusing. And the algebra is, it's time consuming and difficult, and it doesn't really, well, there are much easier ways to do it. There is a series of classes in college you can take that deal with how do you solve big systems like that. Which, by the way, this is not a really, well, how to say this is one of those things in this class that you'll use again. A lot of this stuff, if you don't go into math, I agree. I mean, it's it's making your brain stronger, but you may not do a lot of complicated algebra depending on what your career is. But you will do linear regression, for sure, at some point. And it's likely you'll do some of this. This is when you want to deal with a system where there are lots of variables simultaneously. This is oftentimes how it's done. So when you're simulating something, you don't want to do this algebraically anyway because it takes so long. There's a mathematical approach called matrices, which allows you to take linear systems and do all the algebra tricks using some rules. The matrices are just these ordered rows and columns of numbers and variables, and you can just look at those things, and there's these complicated rules for how you can swap rows out and do all kinds of fancy stuff and get answers, but we're not going to do that. That's a much more complicated topic. That's for college. The good news is that calculators now can be that for you. In fact, a lot of these linear algebra classes are starting to kind of dwindle because why would you take that shortcut from doing the algebra anyway and not let the calculator do the row manipulations, all the row operations? And so we'll be able to just enter this stuff eventually. Long story short, by the end of the unit, we'll be able to take a linear system and enter it as a matrix and let the calculator quickly tell us what the solutions are. Okay, and we can take arbitrarily big systems. We could do a 10 by 10 system and do that in almost the same amount of time it takes to do a very small system on the calculator and get the same result, whereas doing a very simple 2 by 2 system algebraically might take us 5 minutes. Sure, it's no big deal. But doing it 10 by 10 might take us 20 hours, and we don't want to probably do that. Maybe I might make some exceptions and have a few people work on this. Just he seems enthusiastic about it. So I'll probably see if you want to take a weekend maybe and see if you can knock one of those out for us. But I want to send it to everybody, just a handful of people.
Like one of the last time over here.
Okay. Well. So this will be a good shortcut for us. The easiest way to do these is, honestly, even the really small ones, the easiest way to do them is just graphically. Graph them on a calculator and find the solutions that way. And that's what we're going to look at today. But you'll have to do these without a calculator also. So, yeah, I didn't choose that, but it's kind of tranquil, isn't it? So systems of two linear equations and two variables. We'll just use x and y. So here's what a system is. It's just two equations taken together. So it looks like this. Now we got two linear equations here. They might be written in slope-intercept form, y equals mx plus b form, but they might not. Usually when we're doing this kind of stuff, we actually like to write them this way instead. We like to write them in standard form. ax plus by equals c, dx plus ey equals f. Now a, b, and c are just numbers. In fact, they're integers, so they're non-fraction numbers. We'll talk about how to solve this algebraically later, but just before we get into how to solve it anyway, that's what a system looks like. That's what a system means. More than one equation taken together. Now let's talk about solutions. If I were to give you just a line, let's just take the line, how about 2x plus 3y equals 6. Somebody tell me, what does it mean to be a solution of that linear equation? Just this one right here, by itself. What's it mean to be a solution of that equation? What's it going to look like? Okay, well, the graph looks like a line. But if I talk about the solution, what's the solution going to look like? Coordinates, yeah, it's going to look like x and y coordinates, aren't they? The solution is just going to be, I'm going to get a number for x and a number for y. A number for each of the two variables, right? Can anybody see an example of a solution that would work there? What do you think, Chance? Yeah, there's one. There's a solution. X equals 0, y equals 2. How do you know that's a solution? What's it do? It makes it a solution. Okay, yeah, it makes the equation true. If I plug those values in, I get 0 times 2 plus, or 2 times 0 plus 3 times 2, I get 6 equals 6, right? So it makes the equation true. We say in math it satisfies the equation, so it is a solution. Are there other solutions? Anybody think of another one?
Yeah.
What do you think?
X is 3, y is 0.
Good, there's another one. How many are there total? Those that we've named two, could I get others?
Yeah.
How many solutions do you suppose there are to this linear equation? Infinite, right. And if you think about what these are graphically, these, just like 0, 2, just corresponds to, those are coordinates, right, of a point. That corresponds to a point that sits on this line. This is a different point that sits on this line. How many points total sit on that line? Infinite. Each one of those points would have a set of its own coordinates if I wanted to find them, right? And they'd all work. So there are an infinite number of solutions to this thing. Now, what do you suppose the solution of a system would look like? If I've got a system of two equations. They're both lines, right? And so the solutions ought to look kind of the same for each of those, right? But a solution of the system is going to be just a little bit different. A little different meaning to it. Any suggestions about that, what that might be? What do you think? Say it again. We want to know what the solution of a system might look like. The solution of a line, we had a whole bunch of ordered pairs. What do you think, Melissa? Ah, how about that? Now look at it that way. Okay, we know that if I look at the graph of both of those equations, they're both lines. If I draw the two lines, presumably they might intersect somewhere. Now, how many times can lines intersect? Once. Okay, so how many different solutions? It's probably going to look like an ordered pair, right? An x and a y value. How many this time would I expect to get? Just one. Just one. Because this time, I'm looking for that one special ordered pair that works in both of these equations at the same time, which corresponds to that one point that's contained on both lines, the intersection, right? Now, it's possible we could get some other things happening. Maybe the lines don't cross. Maybe they're parallel. And then, how many solutions am I going to get? 0, right? What if the lines overlap completely? Infinite. Then every point on one line is also on the other line, right? So there's some other kind of weird things that could happen, but sort of the, the normal thing is that they cross once. Oops. Yeah. So an ordered pair that makes both equations true. And if we want to just quickly, let's take an example here. What if I check, I've got these two possibilities. I've got the ordered pair 1, 4 and the ordered pair -5, 0. If I try 1, 4 on, in that first equation, try it on for size, I get an answer that doesn't work. When I plug 1 in for x and 4 in for y, I get the result -11 equals -5. So is there any way that could be a solution to the system? No, you can't. If it doesn't work in the first equation, we don't even care if it works in the second one. Right? It can't work for the system, because it has to work in both to be a solution of the system. So what about this guy over here? If I plug in -5, 0, I end up with the result -5 = 5. So it works in the first equation, but it's got to work in both. Try it in the second one, I get the result 10 = 10. So yeah, that is a solution because it works in both, right? Okay, so now solving a system graphically. We'll get to algebraically later. Must have calculators, and let's talk about how we do this. We're just going to graph the equation on the same coordinate plane, so on the same graph, and we're going to look for where the lines intersect on the graph and calculate. Okay? And then we'll talk about at the end. Well, I'm just going to look at 3 quick examples, one of each kind. We'll look at one where they cross, and then one where they are the same line, and one where they're parallel. We'll look at how we could deal with each of those situations on the calculator. So let's try this guy. Let's see, where did my... Lost my calculator. Okay, so here's how you do this. On the well, what do you think? How do you suppose you probably do this on the calculator? You could guess. Yeah, it's got to graph the 2 lines and find the intersection. Now there's one condition on this though. In order for the calculator to find the intersection, you have to be able to see the intersection on the screen. And so that sometimes, if you got 2 lines that you can see are going to cross, but they're not crossing on the screen, you might have to tweak the window a little bit. So, make the window bigger to go find where they do cross. Okay, so now here, this is a little bit tricky though. I want to clear everything out. I want to make sure I've got no plots and nothing. I want to just have 2 lines and that's it. So clear everything else. Now this is a good little trick to learn here. It's not a big deal. Notice that these 2 lines are not written in slope-intercept form. So they're not solved for y, right? I could, on paper, just solve these things for y and then enter those into the calculator, but there's a quick little shortcut you can do that works well. You can solve them into the calculator because the equation that you enter on the calculator doesn't need to be fancy. It doesn't need to be simplified. It just has to be correct. So now, what are the steps I would go through in this first equation to solve for y? In order, what would I do first? Okay, I'd subtract 2x and then divide the whole thing by -2, right? So if I'm going to do that on the calculator, the thing you can't forget to do is I need to open a set of parentheses. Because after I get everything over to one side, I've still got to divide by -2, right? And so now I've got y equals some stuff on the other side in the calculator. What's already over there? -8. So I'll put the -8 there. What am I going to push over there with the -8? Okay, so I'm going to subtract 2x to that side. Then what do I do? Okay, I'm going to divide, but before I divide, I have to close the parentheses, because I have to divide that whole quantity by -2, right? So first I'm going to add terms to the other side, then I'll close the parentheses and divide. So divide by -2, and that's it. I don't have to simplify that. That's good enough for the calculator. So what's the second one going to look like? Tell me the exact buttons I should push on the calculator. Parentheses, open parentheses. 4 minus 2x. Close parentheses. Divide by 2. Perfect. Okay, we got that? Now what? When I want to graph it, what do I do?
Graph.
Well, I don't want to just push graph because I don't know what the graph's set at. I'd like to reset it maybe. So what do I do to reset the graph to its normal standard position? Zoom. Standard? Zoom 6. And hopefully I'll see the intersection. If I do, great. And then I don't have to tweak it. If I don't, I might have to make the window bigger. Okay? So I can see the intersection. Now this part is really simple. To find that intersection, all I have to do is I'm going to go second calc 5 for intersect. Okay, then the calculator is going to ask me 3 questions, all of which I can skip. It wants to know, is the first curve y1? Just in case, what if I had a whole bunch of equations graphed at once, and I want to find a specific intersection. This allows me to pick which two I'm intersecting. But remember, we only have two on there, right? So we can just hit enter. We already know automatically that the first one is one of the lines, the second curve is the other line, so I can just hit enter twice. And now the third question it asks me for is a guess. Now remember why it does that. It does that because sometimes, like if I had a curve, say I had a parabola and a line, those could intersect in multiple places, right? And so I might need to specify which intersection am I trying to find. Okay, but how many times could lines intersect? Once, right?
But it's all right.
Did you make sure you didn't use a negative and you subtract 2x?
That's it. That's it. That's it. It's really easy. The common mistake is to use the minus sign instead of the negative sign, for example. I bet you that's it. Okay, so then my guess, I don't have to do anything with that because the calculator doesn't need a guess. There's only one intersection to find, so I just hit enter again. Just hit enter 3 times. You don't have to even think about it. And it tells me the intersection, -1, 3. Once again, do that again. If I've got my graph, you're going to do this a lot. All you do is just second, calc, 5, enter, enter, enter. And it gives you the answer. Okay? Everybody get it? Okay. Yours not working?
This kind of.
Oh, you didn't get it. Okay. Forgot the x. Right, subtracted 2x. If I go back, remember what I had to do here? Let me go back to that. In case anybody didn't get this, that's what we want, right? Because I'm subtracting 2x over to this side.
How do you get x?
Just the x button, upper, yeah, this is new to you. There you go. Okay. Okay, now I will show you, there's another little shortcut on this, just so you're aware. If you happen to be in the inequal or inequality, I can't remember what they call it, that program, I'll show you what you can do there. You don't have to if you don't want to. You can if you want. I'm going to turn mine on. If I'm in inequality and I graph this thing, graph looks the same, right? But look down here at the bottom after it graphs. It's got these little virtual keys. One of them says POI-trace. POI means point of intersection. So all I have to do is just hit alpha, and then either one of those two buttons is underneath that big wide key. So either one of them will work. And it just gives me the answer. Little. Yeah. So that works. Okay, I'm going to get out of inequality now. Yep. Yes. Okay, so now let's try another one. You got that one. How about this? What if we get, let's just skip through this. Okay, how about this guy? Try this one. Put this one in on your own. Try this. Everybody get that for your... Does that all make sense? Oh. No. Okay.
Wait, on the second one, please.
questions? Anybody have any trouble with that? Zoom 6. Okay, just kind of use the standard. Okay, so now, if I hit Zoom 6, yeah, you just see one line. Okay, now, there's two possible things that could be happening here. What's one of them? Okay, they might be the same line. What's the other possibility?
Calculator's messed up.
Well, okay, maybe it's just off the screen. Maybe one of them's off the screen and one of them's on the screen, right? Now, if we want to be as efficient as we can about this and logical. So let me just do it. So, which one is going to be easier to determine? I could go on a wild, goose chase and try to find that other line somewhere by making the window bigger. But probably easier to just determine, are they overlapping, right? Now, there's a bunch of ways I could do that. Does anybody have a suggestion how I can determine if they're overlapping? Simple, say it again. Oh, you could, right. I mean, we could, if we divide everything by 2, we see that the equations become the same. Right. And that's what we're gonna look at that Monday or Tuesday when we start looking at algebra stuff. On the calculator, can you think of a trick to see? What do you think?
You go back to the line equals thing, and then you go over to thingamajigger, and then you click on that, and it's golden.
You're getting way too technical for me.
You go to that thing on the far left.
Okay.
or
Turn it off.
No, the thing on the way left.
Oh, I can do that. I can do that too. Yeah, that's true. Okay, I can also. I think this also accomplishes what you're saying. I could, if I unhighlight the equal sign, I turn it off. I turn that graph off, right? So now it's only graphing y2 right now. Okay, now watch. If I hit the graph, well, it looks the same. But maybe that's just y2 and y1's off the screen. So how could I tell? Flip them. Yeah. Go to y equals and turn on y1, turn off y2, and okay, they must be the same, right? Because I graphed them individually and it still looked like that. So they must be overlapping. There is, somebody I hadn't thought of this, but a student last period came up with maybe a better solution to this. You can do, well, yeah, I mean, and you can do that. There's another way you can do this, though, on your calculator. You can, if I just go, what the heck did they do? They did intersect. If I just go second, calc, intersect, enter, 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 and it gives me a point that's on the line, then that tells me that they must be overlapping. Because if the other one were off the screen, it wouldn't have done that. It would have given me an error message. Because you can't, remember the intersection has to be on the screen for the calculator to be able to find it. And so, yeah, that tells me right there also that they're on the same screen. And someone else came up with another one that was also a lot better than my solution. If I just hit the trace button, this was really good. If you hit the trace button, at the upper left, it tells you which line you're currently on. I'm on line Y1. To switch to Y2, I can just hit the down arrow. But to go to Y2, the little cursor didn't blip off the screen. It's still on the same line. So they must be the same one. So we got a plethora of choices here. You take your pick. Don't get to use it that often. Okay, does that make sense? Any of those would work if you're doing this graphically. And I don't mean to imply that graphically is the best way. It's just today's way. Okay, so what about this one? Okay, it looks like they're probably parallel. Huh? Well, let's see. So everybody try this one real quick, and this is our last one for the day.
Flying.
Okay, so how am I going to solve for y in that first one?
5 minus.
Okay, in parentheses, 5 minus
But
x
the y is negative.
divided by...
Negative, so it's negative 5x. I mean, negative 5 plus x.
Right, you could also do that. You could just do the algebra too. If I want to just follow that same scheme, I could say, if I'm doing it the same way I've done the other ones, I could just say the quantity 5 minus x divided by negative 1.
Does that?
Yeah, that'll work. That'll work too. Divided by negative 1 is the same as multiplying. So, yeah, so that'll work too. Either way. So, 9 minus 2x divided by negative 2. Whoops. Like that. 2. Zoom. 6. And, well, they look parallel, okay? Do I know they're parallel? I don't, because they could intersect off the screen somewhere, right? And if I, watch what happens, if I try to find the intersection, if I go second, calc, intersect, enter, 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 it tells me error, no sign change, meaning that it's off the screen. That's kind of its way of telling me that. So that didn't tell me much though. It doesn't tell me if they're parallel or not. It just tells me that the intersection's not on the screen. How could I know? How could I know if they're parallel? There's a really easy way to do it. Other than, I mean, we could just check the slopes of both of those algebraically. But the other way we can do it graphically is if I go second, calc, number 6. That's a fancy calculus way of saying slope. Think of the dy dx as meaning change in y over change in x. Then you can remember the slope. So I want to choose number 6, calculate slope. Now I'm going to calculate it first for y1, right? So I'm on the, I can't even tell which one it is, top right, I think it's the bottom, but I'm on y1. If I hit enter, it tells me that dy dx, meaning the slope, equals 1 for the bottom function. Okay, let's try the top one. So I'll do the same thing. I go second, calc, 6. How do I get from y1 to y2? Down arrow. Now I'm on y2. I hit enter, and it tells me that for y2, the slope is also 1. So are they parallel? Yes, they are. How about that? Okay.